Hey, this is the Electronics Lab, and in this video, I am going through the solution to this system of linear equations and solving it by hand. And basically, this system of linear equations came from a previous video where we were doing mesh analysis on a circuit, and we came up with these three equations for these three unknowns. What I've done here is I've converted from these three equations into a matrix form. And this matrix form is a standard form of A times x equals b. So I'm going to go through and solve this system of linear equations using something called Cramer's rule. And this video is not about where Cramer's rule came from. I'm just going to go through the mechanics of using Cramer's rule. And this is the set of equations that I'm solving, or these are the things that I need to solve. So this is Cramer's rule for figuring out x1. It's the determinant of some stuff that I'm going to put in the brackets here. So that's for x1. And so what I'm going to have to do is find the determinant for this matrix divided by the determinant for this matrix. And it's a 3 by 3 matrix. Both of these are 3 by 3 matrices. So there's a fair number of steps, a fair amount of algebra to go through to solve it. Fortunately, to simplify things a little bit, x2 numerator is a little bit different, but the denominator is the same. So if we just call that d, the denominator, I only have to solve that denominator one time. But for the numerator, x2 is, and x3. So my next step in all of this is identifying or filling in the numbers here for each one of these determinants, which I'm going to take from this matrix for the a's and this vector for the b's. Fill it in, and then solve the determinants. Figuring out the determinant for a 3 by 3 matrix is not super challenging, but it's not super trivial either. There's a lot of arithmetic to go through to do it. So basically, I'm going to have to calculate 1, 2, 3, 4 determinants, and since it's 3 by 3, it's not super straightforward. Basically, when you do these by hand, there's a number of different methods that you can use to determine the determinant of the matrix. What we're going to use is the expansion of minors method. So basically what a minor is, it's if you pick an element in the matrix, so let's say we pick B1, the minor is all of the elements that are not in the same row or column. So the minor for B1 are these 4. So this expansion of minors method basically needs to take a value from each one of the rows and columns and then multiply that value by its minor. So I take B by the determinant of its minor. So I'm going to take B1 times the determinant of this, B2 times the determinant of this, and then B3 times the determinant of that. Take those values, add them up, and those values can be positive or negative depending, and we'll see in a sec whether each one of those values is positive or negative. And then that will give you the determinant. So let's start with D, and let's calculate the value of D given this matrix. So to calculate it, the determinant of D, actually D is the determinant. D is equal to, we'll pick an element, A11, and because it's in the first row and the first column, it's the 1 plus 1 is 2, and so that means it's going to be a positive number that we're using here, times the determinant of the minor, which is going to be this part. So that's going to be A22, A33, minus A32 times A23. And then we'll pick A21 as the next. And because it's in the second row but the first column, 2 plus 1 is odd, so that means we have to subtract here. So minus A21 times the determinant of its minor. So that's going to be these two and these two. A12 times A33 minus A32 times A13. And then plus, because we're going to be using A31 next, so that's third row, first column, so that means it's a positive value here. And its minor will be A12, A23, so those two values, minus A22, A13. And that's what D is going to be. That's going to be the determinant of this, or essentially the determinant of my A matrix over there. So I can plug these numbers in now, and I get minus 300 times negative 650 times 450 minus negative 300 times 300 minus 100 times 100 times 450 minus negative 300 times 150. Just closing there, and then plus negative 150 times 100 times 300 minus negative 650 times 150. So all I've done is just taken these locations in this matrix and filled in the numbers here. And now if I plug in all of these numbers and do some crunching in my calculator, some number crunching in my calculator, I get 32,625,000. So that's the determinant for the A matrix that goes on the denominator for each one of these x1, x2, and x3 calculations. And I need to do a similar process for the numerator for x1, x2, and x3. One of the bonuses, or one of the nice things about this particular matrix, or this particular set of linear equations that I need to solve, is that the b values for b1 and b2 are both 0. So that simplifies the calculations for those numerators quite a bit, because I'm multiplying b1 and b2 by some stuff, and that stuff essentially just goes away. So I'm going to go through the calculation for the numerator for each one of the x1, x2, and x3 in a slightly sped up form. So b1 and b2 are both 0, so that's going to be 0. This is going to be a positive 0, because it's in the first column, first row, minus 0, plus b3, which is 24, times the determinant of these 4 values, so that's these values. And that works out to 127,500. And this is all divided by that D, which is 32,625,000. And that works out to 0.0938 amps. X2, well, this one is going to be negative 0 plus 0 minus 24 times the determinant of these 2 values with these 2 values in a matrix. And that works out to negative 105,000. And of course that's also divided by D, the 32,625,000. And that equals 0.0772 amps. And finally X3. Well, x3 over here, we're doing the determinant of this, and the values I'm going to pick are the b1, b2, b3 again. And so b1 is 0, and it's row 1, column 3, so it's positive, minus 0, plus 24 times the determinant of this part. So it's a11 times a22, a21 times a12, and I'm taking the values from over here, and that value works out to 185,000. Again, all divided by 32,625,000, and that equals 136.1 milliamps. I guess I really shouldn't have called these x1, x2, and x3. These are actually I1, I2, and I3. So going back to the original circuit from that other video, and you can find the links below or maybe up here, you can see how I determined the values for the current for that particular circuit. I know there's a lot of work going into determining these values when you're solving these linear systems of equations. 2x2 matrices are not too bad. 3x3 matrices are starting to get hard. 4x4 you can see is another order of magnitude more challenging. Fortunately, there's a lot of software tools that can help you solve it. Even Excel can solve these systems of linear equations. And I'll have a video showing how you can use Excel. It takes about 3 minutes to set it up and do. All right, I appreciate you watching. See you next time.